All right. So before I start, I wanted to tell you that I added 2 more examples for vibration absorber topic. Right. Aside from the example we did in class, I added 2 more. You can find those examples, I think, under practice problem document under vibration absorber section on Moodle. You can use those also to practice the topic, and if you want to get a sense of how good you understood different aspects of designing a vibration absorber, those are 2 good examples. I highly recommend that you take a look at those practice problems. All right, so what I want to do today is that this is probably the last topic we'll cover this semester, and that would be something that I really want you to know, and that's Lagrange method. Now, we talked about energy method. You remember all the way back when we were deriving equations of motion for a single degree of freedom system. Now, we've been dealing with systems with 2 degrees of freedom, right? And pretty much you can extend this whole procedure that we have been using, model analysis, finding system response, to systems with higher degrees of freedom, 3, 4, just the matrices become bigger. Now, what I want to talk about is how can we derive the equations of motion for these systems, right? We're going to limit our work to systems with 2 degrees of freedom. How can we derive these equations with an approach very similar, fairly similar to energy method, right? Remember, in energy method, we didn't have to draw for the most part, we didn't have to draw free body diagrams. We were only looking at systems energy and using the kinetic and potential energy of the system, we could derive the equations of motion. Now, we'll do something similar for systems with 2 degrees of freedom, right? And that falls into Lagrange method. Now, Lagrange method, I wouldn't say as opposed to Newton's method, but different from Newton's method. You don't really need to draw free body diagrams, be worried about if you're taking the direction of the motion correctly, if your spring, if you're putting the forces applied from the springs to your mass, if you're putting them correctly, you're doing the, you don't need to worry about that part. It's more math. Right? You are taking advantage of math and the fact that the energy of the system is changing during an during oscillation. Right? Knowing kinetic and potential energy, you can actually derive the equation of motion. How does that work? Let me put it under Lagrange. Move this. Lagrange method. Basically, this is a method to derive the equations of motion for a system with multiple degrees of freedom. So let's put it this way. If I'll just give you the final formula, the equation that you can use to derive the equations of motion, we're not gonna mathematically prove how this equation can be derived. Right? I'll just give you the final form of Lagrange equation. And then we'll practice how can we actually use that, how can we implement that to derive the equations of motion for some systems. So if we have a system, let's say with 2 degrees of freedom, let's call degrees of freedom P1 and P2. I'm calling them P1 and P2, like X1 and X2, right? Just I want something more general. Instead of X1 and X2, I'm just saying P1 and P2. Just 2 degrees of freedom. We can derive the equations of motion for this system using, let's say, just going to give you the formula. So that would be d dt, derivative with respect to time, partial L, partial dl, partial d pi dot minus partial L, partial pi plus partial r, partial dr, partial d pi. I think it's dot. Yeah, it's a p. A weird looking p. So let me just make sure that they are read as p. Pi dot is equal to 0. It's a general formula. Now, what these parameters are, well, obviously I goes from I is 1 and 2. Now, if you have higher degrees of freedom, system is with 3 degrees of freedom, 4 degrees of freedom, this I would go to 3, 4, 5. For each degree of freedom, you have to actually write this equation and find the parameters for the system. That will be your equation of motion for that specific degree of freedom. Now, what are these? So L, let's just start. Well, d dt is just taking derivative with respect to time. Partial d L, partial d pi dot is telling me that we have to take derivative of that L, whatever that L is we're going to talk about, with respect to pi dot. Now, if I is 1 and first degree of freedom, and let's say the first degree of freedom is x1. So you have to take derivative of L with respect to x1 dot, right? If the first degree of freedom, we're looking at first degree of freedom, and that is x1. So x1 dot. Second term, derivative of L function with respect to pi, p if I is 1 and that degree of freedom is x, so x1. And the last term, derivative of r is a different function with respect to the time derivative of degree of freedom I. If it's 1, then it would be pi p1 dot, and if it's if that degree of freedom is x, it's going to be x1 dot, x1 dot. What are these? L is Lagrange function. Right. So let me start with R. Actually, R is something that we R is Rayleigh's function. So let me put it here. Rayleigh's function. I think that's an A. Yeah, that's an A actually. So this is a Rayleigh's function, R. For systems with multiple degrees of freedom, you can represent that as 1 over 2 x dot transpose c x dot, or, well, in this case we have to say p, instead that, or degrees of freedom, or p. So p dot transpose p. This has to do with the damping. As you can say, C is the damping matrix. P is pretty much P is a vector of degrees of freedom, right? In our single systems that we've seen before, it's like x1 and x2, and x1 dot and x2 dot, right? This could be P. This could be P dot for a system with 2 degrees of freedom, that we can represent those degrees of freedom with x1 and x2. P1 and P2 are just degrees of freedom that we were representing with X. Now I'm just being more general. I'm showing it with P. So this is Rayleigh's function, right? For a 2 degree of freedom system, right, you'll get something along the line that P1 dot, P2 dot, right? Your damping matrix C11, C12, C21, C22, what these elements are, depending on what your system is and what are the damping coefficients, and then P1 and P2. I think I'm making a mistake. This is dot, sorry. This is dot, yeah. This should be all velocity. Now, we don't really deal with this in this course. In the scope of this course, we've been only talking about systems with 2 degrees of freedom that they do not have damping, right? We only talked about the spring mass system. We're not going to talk about damping at this point. So this is pretty much always zero. Don't need to be worried about how to calculate this for at least all cores. Just want to give you the general idea what is the full form of Lagrange method, like the equation you need to derive the equations of motion using Lagrange method. This is mainly zero. For examples that we have, we're going to see. Let's Rayleigh function. Now, L is Lagrange function. Lagrange. If you're dealing with conservative systems that do not have damping, systems that they don't have any element to dissipate the energy, you're not going to deal with Rayleigh function. The only function you're going to deal with is Lagrange function. Now, what is Lagrange function? That's something that's not that actually difficult to form. It's basically Lagrange, or L function, is equal to T minus U. T being the kinetic energy of the system and U being the potential energy. So T is kinetic energy, U is potential energy. Back to when we were talking about energy method, just do a quick review. Sources of kinetic energy and sources of potential energy. We are going to form those. We need to find those for any given system to form our Lagrange function. And then the rest is math, just taking derivative with respect to different degrees of freedom and taking derivative with respect to time and form that equation for a given degree of freedom. So a quick review. I will try to fit it here. Right. Sources. Let's see if I can put here. Sources for kinetic energy. Right. Three specific things we talked about. We said a moving mass. If the mass is not rotating, it's just moving, similar to spring mass systems we have. Like we have some mass going back and forth, it's just moving. We said the kinetic energy for that, let's say T translation, because basically it's a translational motion. Translation is equal to 1/2 m x dot squared, or it's better to say v squared, right? Velocity. We've seen it in dynamics. We talked about it when we talked about energy method. So it's basically a translational system, right? 1/2 mv squared. The second type would be a rotating mass. We'll call this T rotation. So 1/2 I, right, mass moment of inertia, omega squared. Now, omega is basically just theta dot, right? Derivative of theta. It's going to be angular velocity. And then we had the final or third situation that we had a mass that is both moving and translating. Right? Translational plus rotational motion. In that case, kinetic energy would be T translation. We basically just add up 1 and 2. So that becomes T translation plus T rotation. So these are our sources for kinetic energy. When we were looking at the system, we wanted to find all the kinetic energy or the relationship for the kinetic energy for a system. Then we talked about sources for potential energy. Sources for potential energy. we had the most important one. If you remember, that the one that we were dealing with the most was the spring. So the spring is basically, it stores kinetic potential energy, and then it releases that energy. That's how the main way of energy going from kinetic to potential, or going back from potential to kinetic in an oscillating system. Right. Most of the systems you've seen, they have a spring, and that's how they store potential energy. So spring, and for that you can say U spring, potential energy for spring is 1 over 2 k x squared. Right. The second one was gravity. So you lift something up, depending on how far you go from the ground or from its baseline, some potential energy is stored in that system. So that would be gravity. So show that with UG, it's going to be mg delta H. Delta H being the height, change in height of the system, m the mass, g is the acceleration due to gravity. I'm not going to define those terms. We are just reviewing these. We talked about these when we were talking about energies, energy method. The last one that we only mentioned, and we said we are not going to actually look further into that, but I want you to be aware it's a source for potential energy, is buoyancy. So if the good example would be if you put a piece of wood in water and try to push it down, this pushing the wood down into water is actually storing potential energy in the system, because the buoyancy force is trying to push this back up, right? Wood is going to, well, at least a typical wood, is going to stay on surface. So if you want to push it down under the water, what happens is that because of the resistance of the buoyancy, or the buoyancy is trying to push it back up, you're storing potential energy into that. So that's why when you let that piece of wood go, it starts going up and down on the water surface, right? Because that potential energy starts being released, right? When you let that wood, piece of wood or whatever floating object you have. So this third source, just know that, is buoyancy. So that would be, oops, buoyancy. So here is how it works. You're given a system. You start with finding kinetic energy and potential energy for the system, and you form your Lagrange function. Now, for each degree of freedom, let's say your first degree of freedom is x1, you use this relationship. Right? Take derivative with respect to velocity of the first degree of freedom, take derivative with respect to time of that, then minus take derivative of Lagrange function with respect to that degree of freedom. And if you had Rayleigh function, if you had damping, something that dissipating the energy, you could use the last term as well. That's how it works. And then that gives you the equation of motion for that degree of freedom, I equal to 1. Then you go to I equal to 2, the second degree of freedom. You already have your Lagrange function, just taking derivative. Let's take a look at an example, see how this process works. Let's start with an example that we have derived this equation of motion. We have derived the equation of motion for that before. Right? That's how basically we started talking about second degree of systems with 2 degrees of freedom. Let's say we have 2 masses. You have M1, M2. Let me just get the notations right based on my notes. So that would be K1. This is K2. And this is K3. Right, this is no friction, so I'll just put it on these 2 wheels. That's pretty much it. And we can write as find the equations of motion using Lagrange method, Lagrange approach, whatever you want to go with. All right, so starting with identifying the sources of energy in our system. Let's just start with kinetic energy, T. I have two moving masses, right? M1 and M2. Let's call this degree of freedom x1 and call this degree of freedom x2. I have 2 degrees of freedom, x1, x2. I have 2 masses, m1 and m2. From all these sources for kinetic energy, I have a moving mass or translational mass. So I have 1 over 2 mv squared. There is no rotation there. Right? Masses are just going back and forth. So there is no disk rotating or some ball rotating. There is nothing there. There is no pendulum rotating around a specific point. So there is no rotation there. So all I have is just two moving masses in this case. So that would be 1 over 2 m1 x1 dot squared, right, the velocity of mass 1, plus 1 over 2 m2 x dot 2 squared. That's pretty much it. That's the kinetic energy for my system. Potential energy, I have K1, K2, K3. So I have 3 springs. No gravity, no height is changing. These are moving horizontally. And buoyancy also is not in the picture. So 1 over 2 for the first spring, K1, x1 squared. So how much this spring is stretched. For the second spring, right, it's between M1 and M2. So 1 over 2 K2 x1 minus x2 squared. Right, the difference, how much K2 is stretched or compressed. Well, whatever is the difference between the motion or displacement of mass 1 and mass 2. And we have the last spring, 1 over 2 K3 x2 squared. Like how much K3 is stretched or compressed? Well, depends on the displacement of mass 2. So we have our potential energy, we have our kinetic energy. Lagrange function is just simply T minus U. So I'll just write it exactly that way. 1 over 2 m1 x1 dot squared plus 1 over 2 m2 x dot 2 squared minus 1 over 2 k1 x1 squared minus 1 over 2 k2 x1 minus x2 squared minus 1 over 2 k3 x2 squared. That's my Lagrange function. Let's see if I can identify it, because it's going to go back to it again and again. All right. So this is, so far, we identified sources of energy and we formed the Lagrange function. Now, next step would be to use this equation, right, to find the equation of motion for each degree of freedom. So for the first degree of freedom, let's put it this way. For, if I can use a better, there you go. For I equal to 1, we have P1, like first degree of freedom. And the first degree of freedom is x1. So Lagrange general form is d dt. Remember, we know no damping. So R is equal to 0. So we don't need to worry about the term for Rayleigh's function. That term becomes 0. d dt partial L partial x1 dot minus partial L partial x1 is equal to 0. that would be the form of what is left or what it becomes, the general Lagrange equation. Right? P1 in x1, so P1 dot would be x1 dot, and we just form the equation. There is no damping, so Rayleigh's function, the third term, just out of the picture. So let's do that. Derivative of L with respect to x1 dot. Look at this expression there, right? This is our L, Lagrange function. Now we're taking derivative with respect to x1 dot. The first term has x1 dot. Take derivative with respect to x1 dot. That becomes, let me write it this way, d dt. That becomes m1 x1 dot. Right? 2 goes back, 1 over 2 multiplied by 2 becomes 1, m1 x1 double dot. We're taking derivative with respect to x1 dot. That's it. There is no other x1 dot. So the rest is just 0. All the other terms, none of them has x1 dot. Since we're taking derivative with respect to x1 dot, remember this is a partial derivative. This L function is a function of x1 dot, x2 dot, x1, and x2. But when we're taking derivative with respect to x1 dot, or a specific parameter, in this case x1 dot, the rest we treat that as constants. It becomes 0. So this is it. Right? Minus. Now, derivative of L, Lagrange function with respect to x1. Right? First and second term, they don't have x1. It's just kinetic energy. They're x1 dot and x2 dot. Third term has x1, so if I write it inside this, is minus k1 x1. Right? 2 goes back. I'm taking derivative with respect to x1 from 1 over 2 k1 x1 squared. The term after also has x1. It's 1 over 2 k2 x1 minus x2 squared. So I take derivative with respect to x1. That becomes minus k2 x1 minus x2. And that's pretty much it. The last term doesn't have x1. It has x2 squared. So nothing comes out of that. Is equal to 0. Now take derivative with respect to time from the first term. Like I'm doing this d dt term right there. This just becomes m1 is constant. This one becomes m1 x1 double dot. Do the multiplication for negative values there. It becomes positive plus. I'm going to move things around a little bit. This one becomes k1 plus k2 x1. And that would be negative, positive, and again negative. Minus k2 x2 equal to 0. This is our first equation. This is equation 1. So this is the equation of motion for first degree of freedom. Look at that. This is familiar. This is what you were getting from Newton's method. And obviously it should be the same. Otherwise, we're making a mistake. Let's look at the second degree of freedom. So for I equals to 2, P2, well, obviously is x2, right? Second degree of freedom. Lagrange function becomes d dt, derivative with respect to time, partial L with respect to derivative of L with respect to x2 dot, right? Because we're looking at the second degree of freedom. So now P is x, P is x2, minus partial L, partial x2 is equal to 0. No damping, so we don't need to worry about the term for Rayleigh's function. So let's do this one. Taking derivative d dt from taking derivative of L with respect to x2 dot. If I go back, look at the Lagrange function. x2 dot, the first term doesn't have x2 dot. The second term has it, and that's the only term with x2 dot. The other ones also don't have it. Take derivative with respect to x2 dot, this becomes m2 x2 dot. This becomes m2 x2 dot. That's pretty much it. Minus, let's see what we get there. Derivative of L with respect to x2. First and second term in L doesn't have x2, so term out of the picture, becomes 0. Third term doesn't have x2 either, so that's also out of the picture. Fourth term has x2. Right? So x1 minus x2 squared. So I have to take derivative with respect to x2 from that term. 2 comes to back, it becomes minus k2, and we're taking derivative with respect to k2. So that becomes, let me move that around. 2 comes here. This becomes k2. Let me have to, all right. This becomes k2. There is minus there, so minus comes out, becomes plus. So k2 x1 minus x2. k2 x1 minus x2. And the final term would be 1 over 2 k3 x2 squared with respect to x2. If you take derivative, would be minus k3 x2. Minus k3 x2. This is equal to 0. I'll take derivative from the first term there. This at the time, with respect to time, would be m2 x2 double dot. Here, if I move things around, we're going to get plus minus k2. So it becomes k2 plus k3 x2. And then we get minus k2 x1 is equal to 0. This becomes my second equation. Again, that is pretty much what you get from Newton's method. Right? It should be the same. Otherwise, there is a mistake. So let's write it in matrix form to just make sure that things are correct, and I didn't make any mistake there. Plus some stiffness matrix x1, x2 is equal to, well, is equal to, there is no force, is equal to, by the way, there is a way to actually deal with the force as well in the Lagrange equation. I just put it pretty much on the right side, but we didn't talk about systems, force vibration of systems with 2 degrees of freedom, so I didn't even bring it here. But you can just extend this and derive the equation of motion for systems under force vibration. So the equation 1, we have m1 right there, and then this should be 0 since we don't have any x2 double dot. Stiffness, we have k1 plus k2. And go back, minus k2. Minus k2 comes from equation first. The second equation, this is 0, this is m2. x1 is minus k2, and x2 is k2 plus k3. So this is my equations of motion in matrix form. Equations of motion in matrix form. So maybe a little longer, depending on how comfortable you are with math versus drawing free body diagrams. If you don't want to deal with free body diagrams, Lagrange method is the way to go. Just basically take derivatives. As long as you form the Lagrange function L correctly using your potential and kinetic energy sources, the rest is just math. Taking derivatives and finding the equation of motion for each degree of freedom. So that's what we got when we were actually using energy, Newton's method. All right. Any questions so far? All right. So far, so good. Let's take a look at an example that is less usual or common, or at least we haven't dealt with that type of system before. I gave you this system as a homework problem to find this to to find its natural frequencies and mode shapes. Remember that I'm going to look at a cart and pendulum system. I gave you just the final equation of motion matrix form, so pretty much the same story. You could find eigenvalues from their natural frequencies and mode shapes. But now let's see how can we actually derive those equations of motion. The reason is different in nature a little bit is that the equations we're going to get is, look at this system right here. This system, remember we're talking about coupling and uncoupling. This system, equation 1 and equation 2 are coupled because of the way the stiffness matrix looks. See, the non-diagonal element in our stiffness matrix are not 0. If they were 0, then equation 1 would have been just a function of x1 and x1 double dot, and equation 2 would have been a function of x2 and x2 double dot. But because we have these terms here, this term for instance there, because of this term, x2 comes into the equation of motion for x1, for the first degree of freedom, right? If we go back, look at this, this is the equation for first degree of freedom. This x2 is there because k2 is not 0. If k2 was 0, then this would have been just a single degree of freedom system, right? We just had x1, x1 double dot. So the same story for the second degree of freedom. We have x1 in the second degree of freedom, the equation of motion for second degree of freedom, right there. We have x1 because k2 is not 0. If k2 was 0, then we just had x2 and x2 double dot. It would have been the simple single degree of freedom system. Right? That's basically what happened when we were transforming into modal space. We were going from a coupled system that in each equation we have both degrees of freedom to an uncoupled set of system of equations that each degree of freedom, the equation of motion for each degree of freedom only has that specific degree of freedom in modal space, and we could solve it easily. So this the problem is this stiffness matrix, right? Because the non-diagonal elements are non-zero, then we end up having coupled set of equations of motion. So stiffness matrix is the reason that this set of systems of equations, this set of equations of motion are not decoupled. They are coupled. They are related to each other. We have to solve them simultaneously. But mass is a good matrix here, right? Mass is not messing with our problems. Mass is m1 and m2 non-diagonal elements are 0. So in first equation, we only have x1 double dot. In the second one, we only have x2 double dot. Now let's take a look at this situation. And that's the pendulum cart pendulum system, where mass matrix is the reason we have a system that is coupled, but not a stiffness matrix. So let me just draw the system right there. So we have a cart pendulum system. Let's put it like right here. Say this is the cart, and it has mass of m. Is connected to some support, stiffness K. It's moving back and forth, and some pendulum is attached to it. I don't know why it's so. There you go. And that pendulum has a mass of lowercase m, I believe. That's how this is where it's attached to the cart. It's attached to the cart. It's a pin, so it can swing. This is the degree of freedom x. Let me use a different color. This is the degree of freedom x, and this is the degree of freedom theta. All right, so the problem statement, you can just write find the equations of motion for small angle theta. Right? The theta is small, so we can make that, we can linearize the system so we don't have to deal with a nonlinear system, like what we've been doing from the beginning of the semester. So let's see what we've got. Kinetic energy, right? We want to use Lagrange method and derive these equations of motions for this system, equations of motion for this system. Starting with kinetic energy. One thing you have to pay attention in kinetic energy, when we calculate the kinetic energy for different masses in the system, the velocity we put there, v, 1 over 2 mv squared, or 1 over 2 I omega squared, those velocities are absolute velocities, not relative velocities. So they are with respect to a fixed reference frame. I remember from dynamics, we had relative velocity and absolute relative is with respect to some specific moving frame, maybe. Absolute is with respect to, let's say, Earth reference frame, right? With respect to fixed system on Earth. Well, Earth is moving itself, but we're assuming that with respect to Earth, as opposed, assuming that Earth is not moving, right? Or, well, we're not assuming Earth is not moving, but we're finding the velocity with respect to reference frame on Earth, and that we call the absolute velocity. Relative would be if I find the velocity of an object with respect to another object that is moving. So the v in that equation is absolute velocity. Let's see how can we find it for this system. Now here's what I'm going to do. I have a cart moving back and forth, so it's translational mass. Right? That's pretty straightforward. 1 over 2 mx dot squared. Now I have two options. I can either look at this pendulum as a rotating object, rotating around this point that is connected to the cart, rotating like this. Or I can look at it as a translational system with some velocity v, as long as I can find that velocity. They both give you the same answer. If I look at it as a translational system and I want to find what is its velocity, it has some velocity v, vector v. Now v, again, depending how much you remember from dynamics, if we have, let's say, reference frame there, we say v is equal to x dot, the velocity of the cart, plus the length of this is L. So I have to put it there. This is L. Plus L theta dot. So this would be a combination of x dot, velocity of the frame, plus relative velocity, the velocity of pendulum with respect to that xy frame. And that would be, let's show it this way. It's perpendicular to L, so it would be L theta dot. Right? So R omega. If you remember, V was R omega, and then we had V for, this is the equation we had. We had VA is equal to VB plus V relative plus omega cross R. Now, if the system is attached to the cart, no omega there, V relative becomes L theta dot, and VB is basically just x dot. Assuming A is the, I don't want to make it crowded there. A is the pendulum mass there, and B is where my coordinate frame is located on the cart, attached to the cart. This is B. I can think about this as B, and then this is A. This is a little bit of dynamics. Hopefully you remember the relative velocity. So V becomes x dot plus L theta dot. As a result, I'm treating this as a translational system. So that becomes 1 over 2 m v squared. Right? Now I know the absolute velocity for the pendulum. Right? Remember, these two are vectors, so they form v velocity. The absolute velocity of pendulum is velocity of car plus velocity of pendulum itself with respect to car. Now, I want to find v squared. Well, v squared would be, well, it's a vector, so v dot v becomes v squared. We can write better v's. It becomes v squared. Now it becomes x dot squared plus L squared theta squared the dot squared plus 2x dot L theta dot cosine the angle between them. Right? It's a vector form. All right. So remember, because we are doing the absolute or the magnitude of this squared, right? So it becomes, let me rewrite that. It becomes x dot squared plus L squared theta dot squared plus 2x dot L dot theta dot, right? Two vectors. Multiplication of two vectors, the dot product of two vectors would be x dot L, right? You can just find that. A little bit of background math. X dot L theta dot cosine theta. Now we're assuming that we said for a small angle theta, so this cosine theta is almost 1. So we can write that as 1 over 2m x dot squared plus 1 over 2m x dot squared. I'm plugging in v squared plus 1 over 2m L squared theta dot squared plus x dot L theta dot. That's it. I have to actually put 1 over 2. It's multiplied. So 1 over 2 m x dot L theta dot. Not 1 over 2. Oh. It's 1 over 2 multiplied by 2 behind this. So it becomes m x dot L theta dot. X dot L theta dot. So I just replaced v squared from what I got to the equation there. Right, this v squared. I replaced it here. The first term is just coming from what we had from before. I didn't do anything to that. The second term is forming all these terms right here. Now, this is assuming it's translational. If it was rotational, you would have gotten the same thing, right? If it was translational, you would have gotten 1 over 2. I'll leave it to you to take a look at that. But the pendulum rotating around a support, remember the mass moment of inertia for that was ml squared. Right? I was ml squared. Then you have to form 1 over 2i omega squared plus 1 over 2 m x dot squared. So you can just pretty much get the same thing. I'll leave it to you to figure that out. If this is the case when you're assuming the pendulum is a rotational, translational and rotational, because it's rotating and translating at the same time, right? It's going, it has a horizontal motion because of the motion of the car, and then it has rotation around the point that is attached to the car. So it's if you look at it as a translational plus rotational system, you can just calculate the kinetic energy that way. You should get the same thing. You should get the same expression as here, right? This expression right there. These three terms. Sorry. All right. So that's the kinetic energy. Now, potential energy, cart is just moving back and forth. Right? There's no change in height. But we have that pendulum now. Right? Remember when we were talking about pendulum all the way at the beginning of the semester? When we had the pendulum, And if this is where it is at some given moment, this is length L, this would be H. We said delta H, this is the ground, well, not the ground, but this is where it is at the lowest point, would be L 1 minus cosine theta. If this was theta, we said this is L cosine theta. So the height would be, since the whole thing is L, right? This is L. This is the motion of the pendulum. So this is L. Since the whole thing is L, if it goes up this amount, given theta angle from the pendulum from the equilibrium point in the horizontal direction or vertical direction, we had L cosine theta looking at this triangle right there. So the H or delta H or change in height would be L minus L cosine theta. And then I factored out L. So it becomes L times 1 minus cosine theta. And remember, we can't make the assumption of cosine theta equal to 1 here, because if you make the assumption right there, then this becomes 0. So for potential energy, we actually had to go with it and make the assumption later on. So potential energy, we have a spring. This becomes 1 over 2 k x squared, right? Plus, then we have mg L1 minus cosine theta. Finally, we formed our kinetic and potential terms. So our Lagrange term is nothing but t minus u. The rest is, again, the same story, taking derivative, following math. The trick or the challenging part is to get your kinetic and potential energy right. Once we get those right, the rest is just math. So we'll have 1 over 2 m x dot squared plus 1 over 2 m x dot squared plus 1 over 2 m l squared theta dot squared plus m x dot l theta dot minus 1 over 2 k x squared minus mgl 1 minus cosine theta. This becomes your Lagrange function. Keep it here. We're going to use this over and over because we want to take derivative with respect to different parameters. Now, once we have this, for I is equal to 1, pi, the first degree of freedom, is x. I have 2 degrees of freedom, x and theta. The first degree of freedom is x. So let's do what we were doing before. Let's write the form, general form, d dt. Well, now we have x, so partial L, partial x dot, minus partial L, partial x. There is no damping, so Rayleigh's term is out. Let's form these. d dt. We have to take derivative with respect to x dot. Looking at L, first term, the derivative with respect to x dot becomes mx dot. Second term also has x dot, so it becomes mx dot. Third term has no x dot. Fourth term has x dot. 1 over 2 this term right here. But, sorry, not that. This is the third term. Fourth term. Right there. It has x dot, so we take derivative with respect to x dot. What is left is just basically plus ml theta dot. Keep in mind, we're taking derivative with respect to x dot, so everything else is treated as constant. It's partial derivative. Minus, let's take derivative with respect to x from our, doing that, from our Lagrange function. Only thing that has x is this term right here. If I take derivative with respect to x, this becomes minus kx. as to 0. So this equation, now we can take derivative with respect to time easily. That will be mx double dot plus, let me write it, oops, let me write it in front. This becomes mx double dot plus mx double dot plus ml theta double dot plus kx is equal to 0. You can rewrite that, just make it a little nicer, I guess. So put m plus m x double dot plus ml theta double dot plus kx is equal to 0. That would be your first equation. Equation of motion for the first degree of freedom, which is x. Now let's do that for the second term. For second degree of freedom, for I equal to 2, P2 is theta. Right? The second degree of freedom would be theta. 2 degrees of freedom. So this becomes, general form would be d dtt or ddt partial L partial theta dot minus partial L partial theta is equal to 0. No damping, so no Rayleigh's term. d dt partial L partial theta dot, looking at my Lagrange function. I'm taking derivative with respect to theta dot. So first term, second term, third term has theta dot squared. So I take derivative with respect to that, it becomes ml squared theta dot. So ml squared theta dot. All right. Going back, I do not have any other theta dot. So that's pretty much it. Oh, sorry, I have this term here. Right. Now the term next to it also has theta dot. So if I take derivative with respect to theta dot, that becomes mx dot L. This is m plus m x dot L minus. I have to take derivative with respect to theta. Let's go back. Looking at my Lagrange function. All right, first, second, third, fourth, fifth, none of them has theta in it. Remember, we are taking derivative with respect to theta, not theta dot. So none of them has theta. Last term has theta. We have cosine theta there. So we have to take derivative with respect to theta from that term. Derivative of cosine theta becomes minus sine theta. Minus cancels out the minus, becomes minus mg, I believe, if I'm not making any mistake, becomes minus mgl sine theta. So I took derivative with respect to this term with respect to theta. Cosine theta becomes minus sine theta. There's a minus behind it, negative behind it, so it cancels out. Becomes mgl sine, minus mgl sine theta. We have a minus sign in the back, so taking that into account. Taking derivative with respect to theta. Oh, take it the way you are more comfortable with. It's equal to 0. So take derivative with respect to time from what we got. Pretty straightforward. Ml squared theta dot becomes theta double dot. Ml x dot becomes x double dot plus, there's nothing there, we just multiply the mgl negative sine theta is equal to 0. This is your second equation. Now we can make the assumption that the system, to linearize the system. Right? Now we can say, because theta is very small, we can say sine theta is almost equal to theta. Right? Sine theta is almost equal to theta, because theta is small. So this becomes ml squared theta double dot plus ml x double dot plus mgl theta is equal to 0. So this is a better form of the second equation, linearized form. That's the one we're going to use. So let's see, let's put it in a matrix form, and hopefully I didn't make any mistake and we get the right equation. This is our mass matrix. We have our degrees of freedom as x and theta, so x double dot theta double dot plus stiffness matrix, x and theta, and we have no force applied to the system, so 0 and 0. So from the first equation, I have m plus m for my x double dot, m plus m. For my theta double dot, I have ml. Let me double check. It's just ml, I guess. I have to check the answers at the end. For the second matrix, stiffness matrix, looking at the first equation, I only have kx. So only term here is k. This is 0, no theta there. Now you start seeing that decoupling, coupling is happening because of mass matrix. Second equation, I have it right there. X double dot is ml. Theta double dot is ml squared. X, well, nothing for x. And I have mgl there. And this is the equation of motion. This is the matrix form of the equation of motion for this card pendulum system. And given that we linearized the system, right, we converted sine theta to theta. We couldn't really write a matrix form for a nonlinear system if we didn't make that assumption that theta is small. So looking at this, now you see the coupling happens because of the fact that my mass matrix is not symmetric. In the first equation, we have both degrees of freedom x and theta because the non-diagonal elements of the mass matrix are non-zero. If I go back to my first equation, you see we only have x, so stiffness matrix is not messing with my equations of motion. But now mass matrix is doing that. Because the non-diagonal element, which is in this case is this one, is non-zero, now I have both x and theta in my equation of motion in the first equation. If that one was 0, these were decoupled. This would have been m plus mx double dot plus kx equals to 0. It's a single degree of freedom system. The second equation, this is the one that's messing with the equation. ml squared. Sorry, it's theta. So ml, right there, this term. If this is the non-diagonal element of my mass matrix. Right? If this was 0, this equation would have been ml squared theta double dot plus mgl theta. Nice, it would have been decoupled. This is a single degree of freedom system. I could just solve it. I didn't even have to take it to modal space and take it back. Now keep in mind that these couplings happen not because of the nature of the system, but because of the coordinate system we are taking, right? We are assuming. Here we took x and theta. Right? For a 2 degree of freedom system right there, we took x1 and x2. Now, you know, coordinate system is optional. You can come to me and tell me that you want to take a different coordinate system. You want to take this as x1 and this as x2. That is fine. Now you write the equations of motion. You will gonna get a different type of coupling. I haven't done this with these equations of with this coordinate system, but you might either get a coupling because of non-symmetry, not non-symmetry, because of the fact that the mass matrix non-diagonal elements are non-zero, or because of the fact that the non-diagonal elements of a stiffness matrix are non-zero. So by changing the coordinate system, depending on what you take as your coordinate system, the coupling changes. It might be because of mass matrix, and there are cases that both of them are causing the decoupling. You have mass matrix is symmetric, but its non-diagonal elements are 0 like this, and at the same time your stiffness matrix non-diagonal elements can be non-zero. So both of them actually are creating this coupling situation that's making our life difficult to solve the equations of motion. So this is something related to coordinate system, not the nature of the system. That's why we use modal analysis. Modal analysis is what? It's just converting the coordinate system from what we have to a new coordinate system that the system is decoupled in that coordinate system. That's what it does, pretty much, model analysis. Uh, as long as you can find those coordinate systems, your physical system, like by just looking, which usually don't exist that easily, uh, you're fine. You don't even need to do model analysis. You can find a coordinate set of coordinate system that make your system decoupled in the physical space. But model space guarantees that it finds a set of coordinate system that decouples the equations of motion, so make your life much easier to solve those. All right. That's pretty much it, folks, for today. I wanted you to be familiar with Lagrange method and how it can be used to derive the equations of motion. If you have any questions,